Nikita Borisov at Nikita's a professor at University of Illinois at Urbana-Champaign. He's done a lot of tremendous work in data privacy, security, anonymous communication. Recently, his research is focused on censorship resistance. He's the co-designer of the off-the-record messaging protocol, and he's received an NSF Career Award and has chaired many other important, data privacy and security workshops. So let's give a hand and welcome Nikita. Thanks.
Introduction. It's nice to be back in Purdue. I see some familiar and some new faces here over the last, I think it's been something like 5 or so years since I was last here. So I'd like to talk to you today about circumventing censorship. Censorship is something that's become quite prevalent on the internet. So in as much as the internet is a great source of lots of varieties of human knowledge, a lot of countries and organizations want to be able to restrict people's access to that information. And so people have been studying censorship for quite some time, trying to understand what kind of information and accesses and sites are blocked in different places. So this is a map. It's a few years old from the OpenNet initiative. And you can see that different websites are blocked based on maybe their social implications. So some people will block things that are considered, prurient. There's a lot of sites that have political content that might be blocked as well. And you can see that there's a lot of places around the world where the users have at least somewhat filtered access to the internet. In fact, most recent estimates show that the majority of internet users are facing some form of censorship when they sign online. One place where you can kind of see it stands out on both maps is China. So I was, recently I was in China for a conference, and in China you get to my hotel room, and a lot of the websites I try to go to are blocked. I try to go to Facebook and get no connection. Try to go to Twitter, no connection. Right? So of course, I'm a heavy social media user, so I can't live without Facebook or Twitter for too long. So what did I do? I used one of my computers over at Illinois as a proxy. Right? So what I did is, of course, I can't go directly to any blocked site, but I set up an SSH tunnel that went very nicely through the firewall to my home computer, or no, actually my work computer rather, and then routed all of my web browsing traffic through there. And this worked pretty well for me. It was able to access anything that I wanted, no problem at all. Of course, there's lots of people who set up these types of proxies for access by people in countries where they face censorship. So there are products like Siphon or UltraSurf that you can download and install on your phone and use them to circumvent censorship. The Tor project runs a network that's primarily intended to fight surveillance of your activities, but as a side effect, it's generally very effective at stopping censorship, because if the censor doesn't know where you're connecting to, which is one of the goals of the Tor network, it obviously would not be able to selectively block your access. Now, of course, the censors are not oblivious to the fact that people are trying to get around their blocking measures. And so what do? They say, okay, well, we'll block websites that we don't want people to access. We'll also block access to the proxies, right? And in many scenarios, this is been going on for quite some time. So, for example, this is a graph from all the way back from 2009 for connections to the Tor network from China. And 2009 was when Tor became popular enough for China to decide, it's time for us to put an end to this. And essentially overnight, they stopped pretty much all connections from China to the Tor network. How do they do this? They said, let's go to the Tor project website and say, what proxies are you running? What Tor relays are available on the network? They find out that that's just information that the Tor network publishes. And they find out their IP addresses and just add it to their firewall list. So it's a very quick, easy fix to do. And this was done through largely IP address blocking. The firewall also sometimes it involves blocking DNS and filtering based on content. We'll focus mostly on IP address blocking in this talk. Now, what would people like the Tor project or like Siphon who wants to provide the ability of people in places like China to access the internet, what is their response? Well, you can start introducing more proxies. So you can say, okay, well, they blocked this one, I'll put a new one up. Now, if you just start a new one and add it to the Tor network, of course, you can say, I'll just go to this public directory of Tor relays and add them to a list. And this can be done essentially in minutes. It can probably block your proxy before it's even available. So something that people have decided is that, well, let's not just have more proxies, but have secret proxies, right? Instead of having a list of these proxies that's published in a website and in a directory, we'll have these proxies that we don't tell everybody about. In Tor, these are called bridges. And so you can, when you run a Tor relay, you have this option saying, I would like to be a bridge. I would like to keep my IP address secretly participate in the network, and have other people connect to me. And so back a couple years ago, the Electronic Frontier Foundation ran this challenge to try to get more and more people to start running these type of bridges. So this works okay. The sensor doesn't learn where your proxy lives. But if you don't tell anybody about your proxy, that's not really all that useful, right? When I was running my proxy on my work computer, it was useful to me only. Nobody else in China or any other country in the world knew that I was running this proxy. In any case, they didn't know the password that was needed to authenticate to it. So it was not something that was promoting internet freedom. It was just something that was helping me, right? Now, if you want to be able to have users in these countries access the internet, they need to find out about where these proxies lie. So how do you do this? You want to have the people who want to access the internet find these addresses, but you want the sensors, the people who run these various firewalls, not to know where these addresses are. And so there are a number of kind of halfway solutions. So if you go to the Tor project website, you can get to a page where they say, we will give you a proxy address that you can use to reach Tor. You have to fill in a CAPTCHA. So I don't know, EZT, this CAPTCHA. You can probably solve it if you have a bigger font. And the issue with this is that, there might be a few hundred or a few thousand of these, I forget what the current number is, in a database that can be given out. Now, if for kind of a sense of scale, China is reported to employ something like 30,000 people in the daily task of monitoring their internal social media services, looking for objectionable posts, objectionable website, and censoring them. So their overall task force for censoring information is at least tens of thousands of people strong. They could easily spare a couple of those people to go sit for a day, solve these CAPTCHAs, and get all of the information out. So not very effective. You can do IP address-based restrictions. You can say, okay, from a given IP address, you can only get, a couple of different proxy addresses. But once again, I, as a lowly university professor, can probably, within 10 minutes get access to dozens of different IP addresses and, a handful of different networks. A country like China has, more IPs than it knows what to do with. That doesn't work. Something that does work kind of well is to use social network information. So the Tor project has contacts in various activist organizations around the world, and they say, through some sort of secure mechanism, they pass out these IP addresses, and then the activists then go and meet in back alleys and distribute these out to all their friends and so forth. And that works, but that only works for a certain scale of the network, right? Of the social network. You might be able to reach thousands of people this way. The problem is that once your social network starts growing, you run the risk of being infiltrated. You can't have a secret that's known by 1 million people. You can do some mitigation of that by trying to assign reputation to the people in the social network. And so there are a few systems that people have proposed, including RBridge, which is something that we built back in 2013 and is actually being prototyped right now by the Tor project for trying to track, exactly how, whether if I give somebody in the social network some proxy information, whether you find that the next day it's blocked, and in that case you might decrease their reputation. But it's still a problem that doesn't scale to the billions of people who might be interested in accessing information that's being circumvented. So we decided to investigate an alternate approach. And this approach, what we wanted to do is we wanted to not rely on secret information. Right? We didn't want to say, let's try to get some secret and keep it to distribute it to everybody who wants to know it, but not the censors. Instead, we wanted to have something that is publicly reachable, but is can still be used to circumvent censorship. And this is something that we are now calling refraction networking. It has had a few other names, and I'll go back to that in a second. But the refraction networking is how we describe it now. The way refraction works is that you have a client on your computer that makes a connection to a site that should be reachable from your country. This goes through whatever firewalls and blocking technology that exists and is allowed to reach out. At the same time, we partner with an internet service provider who lies on the path from the client to this reachable site. And they could be anywhere on the path. I mean, presumably they will be outside the censoring country. But they might be, close to the destination. Maybe, if your reachable site is Purdue.edu, you would put something on the router next to your web server. Or they could be further away. They could be in some of the internet service provider that provides, regional or even global access. And, and exactly where you place them and how practical this is something we're exploring. This ISP partner will monitor this traffic and look for a secret tag. And this secret tag will tell it that even though from all the internet protocol information, this connection says, I am trying to reach this particular benign looking site that the sensor allows through, I want you to go and redirect it or refract the connection to the blocked site that of my choosing. So let me explain a little bit more detail how this actually works. This relies on people using the TLS, Transport Layer Security Connection, which is used to secure all secure web browsing today. And this technology has been seeing great increases in adoption. So something like a year ago, I saw some statistics that say over half of the internet connections are now using TLS to secure their communication. So very common. You will see this all the time when you're browsing the internet now. The way that TLS works is that when you connect to a website, you send some handshake messages. So here there's a client hello message, then there's a server hello message. There's some key exchange that happens. So this is cryptographic key negotiation. And then once this is all complete, you start an encrypted session, and the encrypted session hides the contents of what you're communicating. And this allows us to insert our refraction into the process. So inside the handshake messages, you can insert a little tag. It's a secret tag. And I'll go back to exactly what this tag looks like a little bit later on. That our refractor, this is a little box that is inside your internet service provider, will notice. So we'll see your traffic going to the reachable site. We'll say, oh, this is a tagged connection. It allows the TLS handshake to complete. So everything looks like normal. And then when you start sending encrypted data, it says, actually, I'm going to just hijack this connection and redirect it to the blocked site. And essentially, don't send the traffic to the reachable site. Instead, assume that forward it to the block site, using some decryption along the way. Because the sensor sees the correct handshake message followed by some encrypted data, they are none the wiser. From their perspective, everything looks like you are talking to the reachable site. So refraction networking originally came, it was designed almost simultaneously by 3 different groups. There was a group at the University of Michigan who created a system called Telex. There was another group at BBN who created something they called decoy routing. And then we at the University of Illinois created a tool that we called CERIAS. Now, over the years, what happened is that the name decoy routing kind of stuck. They said people just started calling the whole approach decoy routing. Apparently, I am just very bad at picking names for systems. Nobody decided to call this system CERIAS. I don't know why. So these are all things that were done in 2011. And then there's another key development that happened in 2014, which is a paper called Tapdanced. Let me explain Tapdanced, and I'll kind of explain it in the context, and then explain the rest of the details behind refraction. So our original model for refraction networking is that more or less just what I told you. We would look at the traffic going through an ISP, and we would look for the secret tag and hijack the connection once we spot the secret tag and once it goes to the encrypted session. So we published this, the Michigan people published this, the VBM people published this. Then people started saying, okay, well, this is an interesting idea. I'm curious whether it could ever work. So the Michigan people, they were friends with an ISP. And they came to them and they said, hey, we'd like to test this out in your network. And they said, oh, yeah, this sounds interesting. We'd love to participate in some trial that helps censorship. So what do you need to do? And they say, okay, so you see this traffic that goes into your network. We're going to need to take all the traffic that comes in, put it in our box. We're going to look through all of it, and we're going to selectively hijack some of your connections. And they said, are you kidding me? And he said, no. We wrote this code. We tested it. Grad students spent, whole weeks on it. And we'll only hijack the connections to have this tag. We'll forward everything else. And the ISP said, no. This is never going to work. The reason it's not going to work is that this is essentially an inline configuration. You have all the traffic that comes into an ISP, goes to a whole nother box that is, an experimental system, and without spending, many millions of dollars, it's going to remain an experimental system. And that box now decides what traffic goes through, what traffic goes forwarded. If that box is wrong in any way, you're now stopping all the traffic that the ISP forwards, right? This was a non-starter. So instead, they went back and they said, let's see if we can make something a little bit more clever. And so this is what Tapdanced does. What Tapdanced does is it says, okay, instead of having a box that is responsible for forwarding all the traffic, we're going to have a box that just sees a copy of all the traffic. And so the copy is done through a network tap. You can think of you're just like a wiretap, right? And this is something that actually ISPs do support. They do this all the time for network measurement, debugging, various types of operations. Any high-end router has an easy capability to create what's called a span port, where it will take traffic going on one port and just send a copy to another. It will still take these packets and route them and forward them in the normal way, but just dump a copy on another port. So then we say, okay, now we need to build a proxy that works just with this copy of the traffic. The way that works is you change the approach just slightly. So you still have a client going through a sensor to the reachable server, and they perform a TLS handshake. This handshake is seen through the tap by the proxy, but is not modified in any way. Now, once you complete the handshake, what do? You are supposed to use this connection to send an HTTP request. You're going to tell the server, say, I would like to see the home page, or I would like to read article number 123. The way that it's done, if you're using Tapdanced, what you do instead is that you send a request, but you don't finish it. You say, I would like to see the web page that is called, and then you trail off. And inside this incomplete request, you also include this secret tag. What happens is that when a website, the reachable website, sees this message, it says, okay, you kind of trailed off here for a while. I'm going to wait for you to complete your request. So it just sits and waits. At the same time, the Tapdanced proxy says, oh, I saw this tag. I'm going to send a response saying everything is fine. This response is encrypted. So from the sensor perspective, it looks just as if it came from the reachable site. Now the next problem is that you then use the same connection to send more data from the client to the proxy. Right? So you say, okay, this is what I actually want to do. You use this encrypted connection saying, I would really like to go to block.com. This is something that is seen by a Tapdanced proxy. Unfortunately, it is also seen by the reachable server, right? So the reachable server received these packets as well. So you'd think it would respond. But in fact, the reachable server says, something is a little fishy here because there's some TCP behavior going on that doesn't make sense, because in your TCP connection, you are adjusting sequence numbers based on data that was sent by the Tapdanced proxy, but not the real server. And so things get a little bit out of sync. And very fortunately, what that means in both the TCP specification and in most implementations that have been tested is that the server just stays quiet. It says, oh, something's wrong. I'm going to ignore this packet. So in just a tiny bit more detail, what happens is that when you send an incomplete HTTP request, you say, OK, get some URL. You put the host header because that's required to be there. And then you add this extra header with the information that we're going to use for the tag. And then this is what happens at the TCP layer. When the Tapdanced station recognizes this tag, it sends an acknowledgement back. It sends a new message back here. And this new message advances the sequence number, the received sequence number, at the client, which means that when the client sends more data over, it will use this advanced received sequence number as an acknowledgement. And this causes the server to ignore the message. It says, this is responding to data I have not sent yet, and I will just ignore it. Now, there's two caveats here. The first is that the data that needs to be sent needs to still be within the window, that the TCP window that the server is willing to accept data for. Which means that there's a limit to how much data you can send from the client to the Tapdanced station and to the server. The second is that the server will eventually decide, you haven't said anything for a while, I'm just going to hang up. And so we'll close the connection. And so we need to be done with this whole process before that happens. Now, going back to this tag, I mean, first of all, how do you embed the secret tag in this message? This data that's inside this header is not the secret tag, because this data is actually going to be encrypted to produce some ciphertext. But the nice thing is that you know exactly how it's going to be encrypted. You know all the keys that are being used. You know the data that's being supplied. So by controlling the plain text, you have some control over what the ciphertext that gets generated is. And depending on exactly which encryption mode you use, it's either trivial or not too hard to make the ciphertext look like what you want by controlling the characters that go into this header. So we can make this data look like we want. So we can make this secret tag. The second thing I wanted to mention is that I said that we wanted to rely on public information only, but we need to be able to send a secret tag, and the secret tag needs to be able to be recognized by the Tapdanced station, but not by the sensor. How do we do that? Well, we use a trick. In fact, we use the oldest trick in the book of public key cryptography, called the DiffieHellman Key Exchange. The DiffieHellman Key Exchange, if you haven't seen it before, allows two people to agree on a shared secret by exchanging messages. So Alice has some secret X, and Bob has some secret Y. They exchange two messages, which is some group element raised to those respective powers. And then they can both compute the shared secret G to the XY by raising the received message to their respective secret. You can also do this exchange. So DiffieHellman originally talked about doing this exchange online. So I want to talk to you, I send you G to the X, you send me G to the Y. But this can also be done in an offline fashion, where you, as Bob, have a public key that you publish and tell everybody, which is your G to the Y. And you have the associated secret key, which is your secret Y. When I want to make a connection to you, I send you my essentially public key, G to the X, and then we both computed our pairwise shared secret. And what you need to do is you need to work in a group where something called the decisional Diffie-Hellman assumption holds, right? And what the decisional Diffie-Hellman assumption says that if you don't know the secrets, X and Y, and you see the public information, so you see G to the X and G to the Y, you cannot tell whether the shared, you can't distinguish this third, the shared secret, from random. And so we're almost there, because G to the Y can now be public information that's associated with refraction networking. It can be published on the refraction networking website. We don't do this now, but we could just publish it there. We could have, hire an airplane to drop leaflets on China that, okay, maybe that's not a good idea, but some way to distribute this. We don't care if that information falls in the wrong hands. The client generates its own G to the X, and nevertheless, the server will be able to compute the shared secret and use this to identify a tag in a message, whereas the sensor, without knowing the secret Y, will not be able to tell it from random. This almost works. There's one last twist that needs to happen, which is that the value that being sent here need to look really random. So there's lots of places in protocols where you send random data. But what you don't want is you don't want this data to have some structure. Now, a lot of cryptographic protocols are based on various number theory tools that send numbers that have various types of structure. So if you use the kind of textbook Diffie-Hellman example, you're going to be working in mod some large integer, and you're going to be working in some subgroup. It's actually very easy to tell that what you're sending is not just random data, but some element raised to some other element that has the right property. So that doesn't work. But what you can do is you can design a special type of cryptographic group. And this is something that is called Alligator in our case. Alligator was something that was designed by Dan Bernstein. It's actually an elliptic curve that has the property that the public keys generated over this elliptic curve, these G to the X or G to the Y, are going to be indistinguishable from random data. And so there's a few small tricks in exactly how to find the curve. You need to make the size of the curve to be an even multiple of 8 bytes, and you need to make sure the curves have some properties that you can't just figure out whether it has something as a point in the curve or whether it's just some random data. But this is something that can be done. I can send you this paper if you want. And then what you end up doing is in this incomplete HTTP request, now looking at the encrypted version of it, you control it so that some part of the encrypted text actually encodes your G to the X, which through Alligator, you take the bits and you convert it to an elliptic curve point. Then you combine it with your secret to generate G to the XY. This is your shared secret. You use that shared secret to decrypt the rest of the tag. When you decrypt the rest of the tag, you get some shared key that you're going to use for later communication, as well as a nonce, some number that actually appears as part of the handshake. So when the client encrypts it, it puts this part of the handshake, encrypts it along with a shared key, and sends it along. When the Tapdanced station decrypts it, if it was a Tapdanced client, you will see inside the decryption that this random number shows up. If it was just a random person using a normal TLS connection, you will get some garbage as a result of this decryption, and it will not match the numbers in the handshake.
So can we use the G to the X from the TLS connection? In the TLS also there is a G to the X and G to the Y values available.
Yes.
Can we use them?
Can we use those if you're using a DiffieHellman Key Exchange? The problem is that if you're that's a good idea. You might be able to make something. You could potentially skip this if you use G to the X from the TLS connection. The problem that you might run into is that different web servers use different types of keys, so it only work for servers that support this DiffieHellman-based key exchange, right? So if you use an RSA-based one, or if you don't have perfect core with secrecy, you can do it. But that's a clever idea. We might be able to save some bytes into that. So the main thing that happens here is that you have something that relies only on public information, allows me to create a secret tag as a client that only the Tapdanced station will recognize, because the Tapdanced station has a secret key corresponding to the public key through the magic of public key cryptography. And that's, we've been enjoying various forms of this type of magic for the last 40 years. So this is how Tapdanced operates. Now, this happened in 2014. A couple of years later, we decided, okay, now it's time to try to see if we can make this work in a more realistic setting. Because we all had, paper prototypes that were written, by grad students working towards a deadline. They kind of worked, but there's a lot of, every time I'd go talk to somebody, they would say, well, neat idea, wonder if it will work, with kind of a lot of skepticism. There was a project that was put together, funded by the U.S. State Department, Department of Democracy, Human Rights, and Labor. And to address this problem, we assembled everybody who had worked on this project before. So there was us from the University of Illinois. There was a team from the University of Michigan who had since then bifurcated, and because one of the authors of Telex and Tapdanced had graduated and gone on to become a professor at Colorado. There were the people from BBN who had since been just absorbed and renamed into Raytheon. As well, we had some ISP partners. The biggest one of those was Merit Networks, which is a regional ISP that handles all the academic networks inside Michigan, or almost all. We had another partner called Siphon. And so Siphon are company or organization. They put together a tool that lots of people use for circumventing censorship. They use a whole array of techniques, but you can actually download an application onto your phone. You can download a client on your computer for accessing the web in censored countries. And so they wanted to use that with us. We also partnered with an organization called Upturn, who did some of our legal analysis and outreach. So they're a policy organization. They have a couple of attorneys who work in DC who look at policy issues having to do with privacy, internet freedom, and so forth. So this is actually a really interesting team to be a part of. There was a lot of people with varying types of expertise, lots of different connections. And we wanted to make this thing work for real. So we deployed Tapdanced boxes to the production networks of two medium-sized ISPs, Merit Networks as well as CU Boulder. In these cases, the way that would work is that we would take their production router, we would get a SPAN port that would connect to our Tapdance station. Our Tapdance station was just a 1U box with commodity components. Cost, I think, somewhere in the order of $3,000, so not a super expensive piece of hardware. It would get the traffic, the tap traffic, through a 10 or 40 gigabit connection. And then it would also have a management interface through which we can both talk to it and through which traffic could be injected into the network. The Merit network, their backbone network, you can see it kind of goes all over Michigan, but it has 3 big peering points, 2 in Chicago and 1 in Detroit. And so we had 1 station in all of these 3 places. Colorado has only 1 uplink to the rest of the world, and it has a router there that, among other things, has an intrusion detection system that already receives a copy of all the traffic. So we said, oh, you know, what's another copy? We got our box added into there. You know, that took a little bit of work. And once again, it got 10 gigabit mirror of all the traffic going in and out of Colorado, and then the management interface for which we can inject traffic. Then there was a fair amount of development effort. So we needed to build something that was stable. And this was, we had a bunch of people, still mostly grad students, though with help from BBN, who has, slightly more real developers working on real salaries. We rewrote most of the Tapdance code. The station was rewritten in Rust because we wanted to focus on having a safe language. We didn't really want to introduce new vulnerabilities in this infrastructure. We also developed a client written in Go. Unfortunately, there were still a couple of thousand lines of C code, mostly for the code that handles injecting new particular packets into the network that are not part of an existing TCP connection, right? We need to be, we can't just use the kernel socket facility to send data in for it, because we need to be kind of jump into the middle of a TCP connection. So some of that code had to be in C. The way that Tapdance works is that you have your tap. The tap goes through a PF ring driver. PF ring is this driver for high performance networking developed by NTOP. One of the things it does is that it will distribute this traffic among some number of cores, and it will essentially use hashing to map different flows to different cores. I think so you can have a completely separate process operating on a fraction of the traffic, because you're handling large data rates. So one of our boxes handled 40 gigabit of traffic through several interfaces. We need to split that among cores and processes. And then whenever we would first only filter out packets that were having to do with TLS on port 443, use connection tracking to identify the particular connections. We would use the tag check on new flows to identify which flows we actually needed to perform routing on. And then use Tapdance to communicate back with a client through this forged TCP socket. The client connection would go back through this commodity 1 gigabit uplink. And then when we were connecting to the block site, we had a squid proxy that was just an HTTP proxy that we would connect to for reaching the site. Also going through this management interface. So we have a big fire hose of traffic going in through the big tap, and then we have a much smaller fraction of Tapdanced traffic going through the 1 gig interface. And then we also had some tools for stats and reporting. One task that we needed to solve is we needed to identify what reachable websites could we use. So fortunately, our colleagues at Michigan have been spending time doing scanning the entire internet and compiling information about all the websites in the world. So if you run a website or if you have a host that has a reachable IP address, you're in their database. So we used this database. We identified the hosts that were served either by Merit or Colorado, and that would have support TLS. We would then check their properties to make sure that they didn't time out connections too quickly and that they didn't use a really small TCP window, so we could actually use them in this setting. We also needed to check that their TLS version was compatible with what we had implemented, because we didn't implement all of TLS, all of the versions in Tapdance, so there are certain kind of suites that we support. And then we would collect these sites and distribute them to the Tapdance client. We found about 400 or so sites total on these networks, which is smaller than I expected, right? You think there's tons of websites everywhere, but once you especially start filtering, I think we started with several thousand that we then had to whittle down based on their server versions, their TLS versions, based on their timeout and so forth. But these ones worked pretty well. Our client was implemented in partnership with Siphon. And so Siphon has this beta program that allows them to take unsuspecting, or rather suspecting users, and inflict various new features on them. And so this is one that they piloted. They had a total of about 70,000 users who, through a remote update, got a client that instead of using whatever normal proxy Siphon uses, started using our Tapdanced proxy. And then we sat back and watched. So this is the total traffic that we observed on all of our stations. So in aggregate, we had the capacity to handle up to 100 gigabits of traffic, and we saw, as you see, up to about 60 or so gigabits at peak across the 4 stations. These are the sessions that people in using Siphon actually established with our Tapdanced station. And so at any point in time, we might have had as many as 4,000 people using it at the same time. This is the traffic that they generated for. So these is the blocked website connections that they were doing. And so at the peak, we were somewhere in a few hundred megabits worth of traffic, web browsing traffic, that people from a censored country were able to connect and download. So one of the things that we found is that at some point we actually started pushing the limits of our infrastructure. The first thing that we noticed is that this traffic, you kind of see there's this big jump in this traffic from somewhere, I guess, over here. I don't know where to point. Over here, you see this big jump. What happened was that it turns out that our station that was handling most of the traffic, this management interface, turned out that it was only 100 megabits and 1 gigabit, so we just completely pegged it. So we did some tricks to redirect the traffic to somewhere else, and we were able to handle more people. But in any case, we were now getting a fair amount of traffic through our stations. The other thing is that we're actually starting to put some load on the website. And what I mean by load, what happens is that every time we have a session that connects through Tapdance, it creates this TCP connection to a web server. This web server then keeps this, it's a very tiny amount of data that gets sent, but the web server keeps the connection open for a period of time. Different web servers have different configurations for how many connections they're willing to keep open at a time. But some of them, it can be as little as 150. So we're getting a little worried. We want to make sure that we don't like knock a website offline by having a bunch of half-open connections and incomplete requests. So we try to limit things to initially 50, and we actually had to go up to, I think, 75 to this load. But overall, we were able to reach about, through our measurements, something like 55,000 unique users per day. So this was the trial that we ran for a week. We're now in kind of phase 2 of this project, where we'd like to expand on this trial and build a larger deployment that can serve a bigger user population. So we're looking at different places that we can put this at larger ISPs. So in particular, we want to look at ISPs that are transit ISPs, through which traffic to lots of different destinations, lots of different potentially reachable sites goes, to both reduce the load on a reachable site and reduce the chance that China just decides to block, the 500 websites that we were using in our configuration, which would block our deployment. This really makes it, this type of deployment will make it much more challenging for us to figure out what reachable sites to use, because that will depend, if you use a transit ISP, that actually depends on both where the router is, but also who the client is, right? The path you take through the internet depends on where you start. And so we're doing some work right now on trying to understand how to make good predictions using both the observations we see at the network as well as the maps that we have.
So regarding the reachable sites,
yeah.
So you mentioned you have around 450 websites, right?
Yeah.
Clients should be informed, some of them, so that they can actually try to go there. The challenge is again similar to the Tor bridges, right? That the
no,
firewall
we tell the clients what sites to try.
But then the assumption is the firewall doesn't know which websites those are.
The firewall could block them.
Yeah, that's what I mean.
Right. So that's what I'm saying, is that we need to. One of the properties of a larger deployment is that if we use a transit ISP rather than an access ISP, the number of reachable sites could be in the tens of hundreds, thousands, right? So, and no one site would be singled out, right?
One more thing, generically, I assume you must be doing, but so idea is that, let's say a firewall decide to just follow the client and try to reach that ISP, and they also know the public key. And in that case, I assume you are dropping some of the channels selectively or something like that. Otherwise, they can. So if the firewall also just try to connect as a client,
yes,
and perform a transaction, then they know that this particular ISP is the one who is helping.
They do, yes. But the question is, what's the? So they would be able to figure this out. This is our thought is that this is something that should work even in the no secret configuration, right? So the sensor knows everything. The sensor has a copy of our client, it has a list of all the reachable sites, has a list of IPs. The question is, how does the sensor respond, right? They could, in the current setting, they could block kind of a small fraction of the internet and do that. What we're hoping is that if we can get better positioned ISPs, it would be at least very costly to block that. There's other ideas that people have thought that, okay, maybe they could change their routing paths, and that ends up being also something that we can model a little bit better once we understand better what reachable sites are visible by what clients. They can do some active attacks, but that ends up being actually really hard. So to work at a country scale, I think actually I heard that Kazakhstan actually is doing inline traffic interception, or thinks of experiment with it. So China does not. China does everything out of line. So if your traffic in China gets blocked, not because they take your packet and stop it, it's because they take your connection and they send reset signals to the server that says, don't, this connection is. Do you have a question? Or?
Two things. One, I have a question, but first a comment on that last one. Basically, once you get to the point where the sites that would be blocked would cause such great public outcry that they're not willing to do so. Now, that's the key, is that you need to have the sites.
Where that point is actually a really interesting question. It would be very interesting to find out.
Yeah, I mean, what is it that you could block that would?
Yeah, so like the very first, back in 2011, there was a deployment of telex in the lab of the people in Michigan, and so they had like a network of like 3 computers that were running a website on it that you could use as your reachable site. That actually got blocked by China. Right? There was a newspaper article about it, and China said, okay, we'll add this to this thing. Because there's no cost to blocking that. Right? Blocking, the University of Colorado Boulder, or blocking all academic websites inside the state of Michigan, that's a larger visibility thing, right? But maybe still on the table, right? Blocking, tens or hundreds of thousands of websites, that's probably going too far. But, who knows? You kind of you push the tiger and see what it does.
I guess on a related note, was there any reluctance to deploy Tapdance because maybe?
Yeah. So in fact, one of the things is that what the people that we worked with were worried about. I think Merritt had this worry. Let me tell you that after the recording finished, because I'm not sure I should be explicitly saying what that happened, so I'd rather that not be on the recording, but I can tell you briefly. Anyway, so the last thing that we're looking at is, I said that this looks, from the censored perspective, like you're connecting to the reachable site. And that's a bit of a lie, because data-wise, it looks that way. But there's also lots of traffic patterns that are associated with a given website that are different for each site. This is, essentially the shape of each website is different. If nothing else, they all have different sizes, right? And so we have been, one of our next research questions is, how can you do traffic shaping to make that problem, make it look similar enough to the real site so that the sensor won't block it? And the question is, what's enough, is actually an interesting research question that unfortunately don't have time to get into right now. Let me just quickly wrap up. So I think one of the things that was really interesting from our perspective is that we were able to show that you can do this at least a medium scale. You can reach tens of thousands of users, deploy in production networks, and have a refraction network work. We've discovered a whole bunch of interesting operational challenges that nobody really even talked about in the original research. So that's been a very good learning experience. So like trying to figure out how to do these reachable sites, how to manage them, how to distribute them to the client. That was not discussed in detail. And there's also one of the things is that we in this trial, we went to try to preserve user privacy as much as possible. We wanted to collected kind of the de minimis information about what's going on. So we have these big aggregates. But something we don't know as much as, what was the user experience like? Were people, when we saw drops of connections, is it because people went to sleep? Or is it because they got really frustrated with the browsing and switched to doing something else? That's something we don't know. So we're going to try to be a little bit more, in our next trial, we're going to be a little bit more cognizant of that. So with that, I want to thank you for your attention. And I want to just briefly thank all of my collaborators. This is a very large project involving all of the Dream Team partners that I've had the pleasure of working with. I won't list them all here, but you can find them, in our paper. Or if you go to refraction.network is our website where you can find out more. Thank you very much.